Good afternoon. This afternoon is what time? There we are. Welcome to the STELR Shape Your Future Careers in STEM webinars. And we are going to hear from Professor Kylie Catchpole today about solar energy. But first, I would like to acknowledge the different places from around Australia where we are all meeting. I am here on Ngunnawal and Ngambri land in Canberra, and we would like to acknowledge the custodians of these lands of which we are all meeting. I pay respect to elders past and present and acknowledge the deep knowledge seeded forever in country, as we are going to be discussing our STEM knowledge today. So the Careers in STEM webinars have been on every week through the term, and we're really excited about our topic today. Just a few housekeeping issues here. If you have a question at any time during the session, please put it in the Q&A box, and you'll find that at the bottom of the screen. The chat box is not going to work. The Q&A one is the one we'll be watching. So any burning questions you have for Kylie through this whole presentation, feel free to put them in there. We will have time for questions at the end, but if something pops up, we might even answer it during the talk. And you will be sent a survey after this session, and it would be great if you can fill that out for us so we know what's doing well and what you might like to see in sessions in the future. And you will also be getting an extension worksheet on some of the extra work of Kylie's and the solar energy in Australia. So look out for that too. So before any more has been said here, we are going to introduce Professor Kylie Catchpole, who is a researcher at the Australian National University, and she will be talking to you about her career in STEM and what she does in her research. Thank you, Kylie.
Great, thank you very much for the introduction. Hi, everybody. It's great to be here. I'll just share my screen. There we go. So I'm going to be talking about the science of solar. I'm Kylie Catchpole from the Australian National University. So we're at a time of enormous transition in energy. We're switching from the old fossil fuels to new types of energy, and it's all happening very rapidly now at the moment. The International Energy Agency put out a report last year and talking about what we need for net zero emissions. And they said that net zero emissions in 2050 requires an unprecedented transformation of how energy is produced, transported, and used globally. So net zero emissions is really mostly about energy. About 70% of emissions are due to energy. And so what that would mean is from today, no investment in new fossil fuel supply projects, none at all. And by 2040, the global energy sector has already reached net zero emissions. That's what we need to reach. Okay, so it helps to get kind of a sense of the scale of the challenge that we're facing here. And when we're talking about the energy transition, it's a terawatt challenge. What's a terawatt? It's not a unit that we're very familiar with. So you may be familiar with watts. So watts are energy per second. So it's a rate of energy uses. One joule is, so 1 watt is a joule per second. So for a laptop, you're using something like a watt of power. For a toaster, you multiply by a factor of 1,000 or so, and then you're talking about a kilowatt. If you wanted to use a small aeroplane, you'd multiply by 1,000 again, and then you're talking about a megawatt. The amount of power that you would get from a coal-fired power station, you would multiply by 1,000 again, and then you're talking about a gigawatt. So what we need when we're talking about the world's power, we multiply by 1,000 again, and then we're talking about terawatts. So for all the world's energy, we're talking about tens of terawatts of power. So how can we do that? Well, there's an enormous potential for renewable energy to do that through wind and through solar especially, to get a sense of what we would need to install. If we were going to have 100% renewable energy, so that means no fossil fuels, we would need around 60 or 100 square meters of solar panel per person, which is actually quite a reasonable amount. That overall would use 0.1% of the world's land. And this transition is already happening. It's actually happening really fast. People don't realize this because, you know, we're only replacing a small amount of the world's energy supply each year, but we're actually installing more solar and wind than anything else at the moment. Around 75% of what is being installed each year for electricity capacity is solar and wind. So this is a dramatic change from recent years. So globally, we're installing more solar and wind than anything else, and in particular, installing more solar. The nice thing about solar is that it's highly modular, so you can install it in a small area or a large area. So this is a solar panel system on somebody's roof. This is around 5 kilowatts. Remembering kilowatts, around about what you need to power a toaster. You could power something like 5 kilowatts. Of course, you connect it to the electricity grid. This will supply all the electricity for a house. You can then go larger. So this is the solar farm out at Royalla near Canberra. It's 20 megawatts of panels, and you can see you can just keep installing them. And you can go larger still. So this is a really big solar farm out at Broken Hill, 53 megawatts. It produces enough electricity for 22,000 average homes, and it reduces greenhouse gas emissions by over 100,000 tonnes of CO2 per year. So that's a really big contribution. And you can see that's also a really big solar farm. Okay, so what about these terawatts we need to transform the world's energy? Well, what we've got here is a graph of the amount of solar that's being installed in gigawatts per year. Now, you will notice it's a log scale graph. We should be well used to log scale graphs because of COVID over the last couple of years. But so on the y-axis, we're increasing by a factor of 10 each gradation there. And we've been installing solar at a rate that increases on average 38% per year for decades. If you have these kinds of growth rates, then you get to high numbers pretty fast. So we're now installing around 100 gigawatts per year. Now, remembering what terawatt is, so 100 gigawatts is a tenth of a terawatt. So within a few years, we would get to the stage of installing terawatts per year. So that's really the scale that we need to actually transition the world's energy system. And you can see all of this stuff is very big business, highly automated. At the moment, you can see all these robots in the factory making the solar panels. And this means a lot more than electricity will transform. We'll also have electric cars, of course, so that will transform the transport sector. We can also have reverse cycle air conditioners or heat pumps. And so that transforms the heating in buildings and can move us away from gas. So the effect of this growth and cost reductions of solar is a lot of scope for emissions reduction through disruption of the oil and gas industries. All right, so that's kind of the context. This is why we're working on these things. This is the kind of problem that we're trying to solve. So what's the science? What's actually going on in a solar cell? So when we shine light on a solar cell, what happens is essentially the solar cell is constructed so that it makes electrons move, and they can only move in one direction. Once they're moving in one direction, they can move around an external circuit, and so they can do work, light up a light bulb, for example, in this example. But essentially, you've got the electrons moving in one direction, and that creates an electric current. Okay, let's kind of zoom in a little bit more. Now we've got a graph of energy versus distance. So this is the energy landscape for an electron, if you like. So what happens is that the light comes in, it moves an electron, it gives it extra energy, moves it up to a higher energy level. Once it's up at that higher energy level, it's only going to go in one direction because it's easier for it to go in one direction. And as a result, you can get some current out of the solar cells. So that's fundamentally how it works. So you'll notice that this is actually making use of the quantum nature of light. You need sufficient energy in the photon in order to excite the electron. If you don't have enough energy in that photon, it won't excite the electron up to that high energy level. So it's really making use of that quantum nature of light. Now, the cool thing about solar cells, one of the many cool things about solar cells, is that they make use of not only the quantum nature of light, but also the wave nature of light in the same device. So this shows you a picture of a solar cell. You can see that it's this kind of blue color, and you get this blue color via an interference effect, which is exactly the same thing that you see in soap bubbles, for example. You get these beautiful colors because of thin film interference. And that interference is because you've got the light coming in and the waves interfere with each other, the incoming and outgoing waves interfere with each other, such that you're only getting the blue light reflected, which is good because we want as little light reflected as possible, right? We would like it to be as dark as possible. Most of the light we want inside the solar cell. All right, so one of the things that we're trying to do in research is to try and figure out how we can make solar cells more efficient, because if we can make them more efficient, we can make the energy cheaper and we can make solar energy cheaper. So I showed you this graph before of we have these energy levels in the solar cell, right? And because we have these energy levels, it means that the blue light is used quite inefficiently. The excess energy is lost as heat. So we know blue photons have more energy, but we don't take advantage of the extra energy of those blue photons. So if we want to increase the efficiency of solar cells, then we have to do something about that. And that leads you to an efficiency of silicon cells in production have efficiencies of up to 22%, something like that. Okay, so what you can do is you can put another solar cell on top of your silicon solar cell. And if that solar cell on top has a higher band gap, then you will take advantage of that extra energy of blue light. You'll get more voltage, and overall you can get more efficiency. So this is what we've been doing in our research. We've been using a material called perovskites. Now, perovskites are really interesting. Perovskite actually just refers to the crystal structure. So I've shown you a picture on the top right there. That's the crystal structure of a perovskite. So all the little circles are atoms, and you can replace those atoms by lots of different things. So that gives you a lot of opportunity to engineer the structure and to make it absorb light the way you want, and to give you the good electronic quality that you need to make a good solar cell. And the other diagram shows you all the different layers in the perovskite solar cell. So there's lots of different layers, lots of things that you have to put together to actually make it work. So this is what we've done. We've made some perovskite cells on top of silicon solar cells. We got over 27% efficiency, and that was the highest value that had been reported. So that's a really exciting way of increasing the efficiency, and hopefully we'll be able to reduce the cost of solar through that increase in efficiency. One of the other things we've done is actually connected these solar cells up to a catalyst to generate hydrogen. So one of the things that we will also need, as well as electricity, we will need some way of having things that can decarbonize other parts of the economy. For example, we use coal in making iron at the moment because you have to reduce the iron ore, and at the moment coal is used to reduce the iron ore, but it would actually be possible to use hydrogen to reduce the iron ore to make iron instead. So one of the things we've done is to connect our solar cells with a catalyst to generate hydrogen, and we're also able to do that with really high efficiency. So that's the science behind what I'm doing. I'd also like to tell you just a little bit about my story and my pathway to getting where I am and to getting into science and engineering. So there's a few pictures of me starting about 10 years old. I was interested in all kinds of things, space and electronics, but also cooking and running. You can see there I am in the top left there. When I was 15, I tried to make a robot but it was not very successful. This was the days before the internet, also before microcontrollers. It was a lot harder. Anyway, I got like maybe a third of the way through and it didn't work. But I still learned a lot, and I learned that I liked doing this kind of stuff. So I kept going. I did a degree in physics. So there I am, bottom right at about 20. At that point, you can see I was interested in floating down canyons on lilos. I also wanted to discover the secrets of the universe. I was really excited about particle physics and astronomy, and I also wanted to help the environment. I really cared a lot about that, but I wasn't really sure how to go about it. And then at the top right, there's me at about 26. I had just finished my PhD in engineering at that stage, and I was working on solar cells, and I was really excited to do that because it combined my interests in physics and also in doing something to help the environment. So now, my life is obviously not just about science. I try to make sure that there's space in my life for doing all kinds of things that I care about. My family, for example, walking in nature, doing triathlons, teaching, the research, all of these are expressions of the things that I really care about. So I think it's important to see that, the people are not one-dimensional, and it's okay to have a range of interests. And now I just want to spend a couple of minutes talking about what doing science is like, because sometimes, in school, your experiments, they don't always work, but I would say that they mostly work. Whereas when you get into research, basically they mostly don't work. And it's a process that you have to get used to and know that this is actually the way it's supposed to be. So what is doing science like? Some nice quotes here. In research, the front line is almost always in a fog, by Francis Crick, who discovered DNA, so he should know. Research is the process of going up alleys to see if they are blind. So trying lots of things, being confused is very normal. This is what you feel like most of the time. You're trying new things, they don't work, you try and figure out why they don't work, and you keep going. Some of the time you're not where you think you are. This is an example from orienteering. So I did a fair bit of that when I was around 10 to 12 or so, where you're trying to figure out your way around a course by using a map and compass. And sometimes you're in a completely different place than you think you are, and you can be very wrong and not realize. Sometimes for years, we found that with some of our previous work on little particles on solar cells. We thought they wouldn't transmit any light. It turns out they did transmit the light. If we'd just done the experiment, then we would have realized, but we didn't. So you can spend a lot of time being wrong and not knowing, but that's also all part of the process. As I said, lots of things go wrong. So your experiments basically constantly going wrong in some form or other. So you need to be constantly optimistic. You need to go, okay, this time my experiment's really going to work. Okay, no, this time. Basically, you need to be learning from what you're doing all the time. And I particularly like Winston Churchill's quote there: success is the ability to go from one failure to the next with no loss of enthusiasm. Okay, so just to summarize, the world's energy system is going through a tremendous transformation now. It's actually the biggest transformation since the Industrial Revolution. We've never seen anything like it. But it's not just going to happen by itself, right? It won't be straightforward, but it has to happen. There's a lot of problems that still need solving, and it will occur in the next 50 years. It has to occur in the next 50 years. I think, we have global agreement on that. It's going to require new skills, new thinking, new technology. It's going to need innovation. So we need highly skilled engineers and scientists to actually make that future happen. And that means it's an excellent time to beginning a career in STEM. So thank you, and I look forward to your questions.
Thank you so much for that, Kylie. It was great. Even I didn't realize how quickly that trajectory is happening with the solar and wind investment and building. I think that's feels a little bit good that we're moving in the right direction towards the right factors of it. So definitely, yes, if you have any questions, put them into the Q&A box you can find at the bottom of the screen, and don't be shy. All questions are good questions around here. But, oh, we have had the first one. Let's see what this one is. So Lucia's asked, have you heard of a Dyson sphere?
Dyson sphere? No, I haven't.
I will definitely need to Google that one. Maybe we can get a bit more information on that one. But I had a quick question at the start. That was physics at high school versus physics you've done past that. Did you enjoy it? Did the high school physics really kind of get you involved in it, or was it vastly different to what you're doing?
I guess it was a mixture of what I was doing at school and kind of extra reading that I was doing at home. So you know, everything I learned at school was super interesting and useful, and I always had extra questions about, you know, how things worked. But it was also really helpful to just read a bunch of popular science books and to learn about the possibilities. This is why I was so interested in quantum mechanics and astronomy and things like that, and sort of looking at the different possible directions. You know, in retrospect, I would have read it, I guess, a bit more broadly. And one of the things I've discovered is that, you know, when you do something like a degree in physics or engineering or maths, any of these kinds of areas, you get these broad quantitative skills and you can apply them in all kinds of areas. So for example, you know, you could, with those kinds of skills, you could also do ecological modeling, which would also be an important contribution. So there's lots of different ways you can go, and just because you've done, you know, you have to choose obviously some degree path, but that doesn't even constrain you to that area at all.
So one of the questions that's popped up is about solar panels. We talked about them being modular and so you could fit them to a space. Can they be flexible in shape, particularly your kind of double layer ones? Is it limited to this being flat, or is there a shape we can do it?
So your standard solar panels, they're based on silicon, which is a hard material. It's like 1/3 of a millimeter thick or so, and they have glass backing. So your standard solar panels are not flexible, but it is possible to make flexible solar panels. In general, there hasn't been a particularly compelling niche for it. So sometimes people make solar panels for architectural applications, and so you can make them, in that case, you can adjust them so that they're curved and things like that. But generally, if you just want as much power out as possible, as cheaply as possible, the standard types are better for that.
Yeah. With the solar farms, you showed the one at Whyalla and then the one at Broken Hill. Is there potential for those to become a bigger thing, particularly in Australia, where we have a lot of kind of free space to do that? Or is there a kind of a size that becomes limiting on them in space?
There's not a particular limit on size. The thing that creates the limit is actually the grid connection. So you need to, so you want essentially a relatively large amount of not too expensive land, but you also want to have a strong grid connection. And so that sort of limits where you might put it. So one of the things that we need to do as part of this big transition is actually increase the amount of transmission that we have in this country, so we can actually get the electrons from where the solar and wind farms are to where people are in the population centres.
So what was the kind of factor that got you into working with solar cells? Was it like, obviously, what drew you into working particularly in this area?
It was that combination of doing something important for the environment and my interest in physics. So I was essentially looking for something that might help and that might make a difference. You know, I looked also at, for example, at fusion research at the same time, but I felt that solar cells were more promising, you know, and that turned out to be a good call. You know, I've been surprised, I guess, at how rapidly solar has developed. So that, you know, all of these things are kind of lucky. You have to choose which seems most promising. Of course, there's opportunities to shift as you go. If you think, you know, something that you think was going to be a good direction to go, and turns out you want to do something different, you can always change direction. But yes, there's a huge amount of opportunities in solar in particular.
And and with that, do you think you would have been good to do robotics kind of instead of this, given that there's a little bit of, you did try and build a robot when you were 15? Do you think robotics might have been equally kind of attractive, or, you know, in the future maybe?
Yeah, well, I did get to build my robot because I've been teaching the first year engineering course, and in the first year engineering course we build robots. So I did in the end get to build my robot, which is a lot of fun. So yeah, it's great, and it's great to have students come in and be able to immediately build a robot, even if they've done kind of nothing particularly technical before that. You know, personally, I have that strong motivation to do something to help the environment. I feel like climate change is the biggest challenge that we're facing. So for me, it would always be something to do with energy. I mean, different people have different motivations. So I think that, and that's something that's important to recognize, I guess, when I got towards the end of my physics degree, and I was doing some more pure physics research. And again, you know, for some people that would be the right step, but I realized, no, for me to be motivated, I have to do something where I feel like I'm helping solve the world's problems.
Which is, yeah, I think it's a big thing that science and STEM does is it's a problem solving, and it's just, you know, finding solutions for what the world needs. And there's a lot coming up in the future with all of this. There was something in my brain. I'll switch to this question, the other one will come back to me, but was there something when you were at high school, is there a piece of advice you wish you would be able to have given your high school self, that now in hindsight you kind of think, yeah, I should have known that?
I guess I've oscillated at times with how I've felt about doing science. Well, I think when I was in high school, I was pretty confident. People said, oh, there might not be many jobs. And I thought, well, I only need one. So that was possibly overconfident. Research can be difficult. And there's been other times when I felt, you know, early in my academic career, it's felt difficult to continue. It's felt really competitive. I wondered if I could do it. I think then the advice and the sort of key message I try to get to students now is that there is an important way you can make a contribution. You know, regardless of what happens, regardless of the opportunities, there's always a way that you can make a contribution. Even if one particular path turns out to be not open to you, there's always something you can do. So the key point is, rather than thinking, oh, am I good enough to do this, I realized that that's just not an interesting question. And the more interesting question is, okay, how can I do something to help? And you know, what's the path forward for me to do something to help?
Yeah, for sure. Don't forget, you can put all of your questions and ideas in the Q&A function. The chat one's actually shut down, so make sure it's all in the Q&A, otherwise I will miss it, and I don't want to miss any of your questions. I had a quick question about your perovskite chemical, I guess, how did you kind of come across this structure that helps with this efficiency? Where did it come from, I guess?
This, I guess, is part of the very distributed nature of research. People are trying all kinds of things. They're originally tried, I don't know, sometime maybe 20 years or so ago. in light emitting diodes, and they didn't get very far, and people tried it and thought, oh, it's kind of interesting, and then it sort of died out. And then somebody tried it only 10 or so years ago into a really different kind of solar cell, and they as in a quite different role, but it turned out to behave surprisingly well. And so people didn't understand it, and so everyone started getting excited about it. And it's, you know, just one of these really interesting things where it behaves a lot better than you might expect. The material itself is actually full of defects, so there's atoms, you know, really where they shouldn't be. And normally in a crystal, that means that the electrons really don't want to travel through it. Just because of this, you know, particular nature of this crystal, it has this kind of self-healing property. So it's constantly kind of being damaged and reforming itself. So it turns out that it's not sensitive to those defects, and it has really nice quality despite that. So a bunch of interesting properties of these materials. And as I said, you know, there's lots of scope to change atoms and move things around. So there's basically a lot of researchers around the world at the moment trying all kinds of things and figuring out what works.
Oh, that's great. Could it be retrofitted to existing silicon ones, or is that kind of a little bit beyond the scope at the moment? Am I getting too far ahead?
No, it's something that would be put into new panels. So you would be depositing the material onto a silicon cell, but it would have to be part of the whole process flow for making the standard, for making the silicon solar cells.
Okay. I think one of our kind of guests is trying to send us something, but please send it in the Q&A section. You can read it all here. So obviously they're quite keen about your work. They can just tell us something. So talking about the collaboration around the world, do you collaborate with other sections, or is your team wholly here in Australia, or are you working with other people around the world, or just kind of sharing results and things?
Mm-hmm. So we have, at ANU, we have about 60 people working on solar cells. So that's actually important in itself. We have a big group, so that everybody, we share. We have very expensive equipment. We share our labs, and we share all our ideas between the people that are working here. So that's one element of it. We also have collaborations with a bunch of different groups around the world. So we might share results and work on research together, discuss things together, and then also we exchange information at conferences. So all of these things are important. And, you know, I like to liken this is to a little bit to how bees work, right? We're a social species, just like bees. And what bees do is that they fly out from their hive and they find some interesting flower, and they bring back a bit of nectar, and then they tell all the other bees about it, right? They actually do this kind of little dance. If you can, the science of it is very interesting, actually, bee communication. But they tell all the other bees about it, and then the other bees go out to get those flowers as well, right? So science is the same. It's not enough to actually do the research. You need to be also sharing your information, then other people can work on it. And so you can get a big community of people all working in the same direction. That's where you can get really exciting things happening.
Yeah, and I think that's the really good thing about science, right? It's not just your group of people here, it's everybody else doing their little bit, and everybody does
it's that combination, right? I mean, a lot of people who work in science like to work, like to do things by themselves, which is totally fine. As a researcher, you get plenty of time to work by yourself, and many of us are introverts and like to do that. But also we have the opportunity to work with other people, and that's fun and inspiring and helps keep up our enthusiasm.
I'm just going to hit this. I mean, Lucia, you said you put your ideas in the chat, but I can't see it in my chat. So you've either sent it to someone else and not me, or you've sent it into another chat panel completely. It's obviously lost somewhere, but we're not missing it. We just can't see it, unfortunately. So hopefully maybe you can send it to us in an email and we'll answer it offline afterwards. So we can, try and get to the bottom of that in this Dyson sphere question as well, which is also pretty good. I guess that's what all of my questions and what we've managed to pull off the other rest of the chat. And I'm really excited about this kind of increasing efficiency on solar panels that we're going to get, and we're going to get a whole lot more around the country as well. So I might bring us to a close there and say thank you very much for your time today and sharing your work and your journey with us. Please don't forget to fill in the survey that you'll receive after this session, and also to look out for the worksheets as well. So thank you again, and thank you for joining us for Shape Your Future.
Thanks. Bye, everyone.